Right now, the industry default for multi-agent systems relies on heavy programmatic orchestration. Developers build complex Python frameworks to manage agents, route messages, and juggle memory buffers. But this infrastructure carries a significant engineering tax. Every time you want to swap a prompt or change a workflow, you have to modify application code and redeploy the entire system. These frameworks also hide the system state. The LLM's context window fills with routing instructions and logs, creating hidden token bloat that degrades the model's focus. For sequential workflows, where humans need to review output at each step, code-heavy orchestration is the wrong abstraction. We are treating AI orchestration as a software engineering problem, when it is actually a data organization problem. The alternative already exists on every machine. We can use the standard computer file system as our orchestration engine. This approach is called the Model Workspace Protocol, or MWP. Instead of programmatic nodes, it uses numbered folders and plain markdown files. An agent simply reads the right text files at the right moment to know its role for that specific step. This architecture is derived from the physical constraints of LLM attention and token limits. By treating context engineering as a file system architecture, we structurally eliminate the bloat and fragility of code-heavy agents. Language models are limited by an attention bottleneck. When relevant data is buried in the middle of a massive prompt, the model often fails to retrieve or act on it. If you supply an agent with every possible tool and instruction at once, you degrade its reasoning capabilities. The model has to sort through the noise before it can execute. Loading 40,000 tokens when a task only requires 4,000 is an inefficient use of the context window. This chart shows the composition of a monolithic prompt. The red section represents the irrelevant context that the model is forced to process alongside the actual work. The fix is to isolate the workflow into discrete stages. By limiting what the LLM reads at any given moment, we keep the context focused and the model efficient. This architectural scoping handles token bloat before the data ever reaches the model. You don't need algorithmic compression if you stop loading irrelevant files. We see this same principle in modern software development through the vertical slice architecture. Instead of grouping files by technical layer, a vertical slice groups everything needed for one feature into a single directory. An AI coding agent only has to focus on that one folder to understand the task. Traditional layered architectures force the LLM to read across the entire codebase just to find the relevant parts of a single feature. We must apply this same organization to our agent workflows. Whether the agent is writing code or generating content, context should be isolated into self-contained, domain-specific silos. The Model Workspace Protocol executes this through a strict 5-layer hierarchy. It starts with a root folder and a global identity file. This file orients the agent, telling it where it is and how to navigate the workspace. The workflow is divided into sequentially numbered folders. Each folder contains a stage contract, a markdown file that defines the inputs and process for that specific step. Inside these stage folders, the architecture enforces a strict division between rules and artifacts. The first subdirectory is for reference material, or Layer 3. This is the factory configuration. It holds the static material like voice rules, style guides, and structural templates. The model must internalize this material as a set of boundaries. It dictates how the agent should behave. The second subdirectory is the output folder, Layer 4. This is the product. It holds the dynamic working artifacts produced during the run. The LLM processes this Layer 4 data strictly as active input to be transformed. When you mix instructions and data in a single prompt, the model has to guess which part to obey and which part to process. By separating them into directories, we remove that ambiguity. This structure determines how data moves between folders during a run. When stage 1 is complete, it writes its output to a plain markdown document. This document is then linked as the input for stage 2. Because the state is just a file on a disk, a human can review and edit the document before the next stage begins. The stage 2 agent simply reads the edited version. This mirrors the Unix pipeline philosophy from the 1970s, programs that do one thing well, using text streams as a universal interface. It also follows the logic of multipass compilers, transforming source material sequentially through readable intermediate steps. By utilizing plain text files, complex state management is replaced by a reliable sequence of file reads and writes. The file system architecture shifts human-in-the-loop oversight from code review to document review. Because every intermediate state is saved as a plain text file, the system is observable by default. You don't need a dashboard. You just open a folder. This chart tracks human intervention. Oversight follows a predictable U-shaped pattern. Editing peaks at stage 1, where the human sets the initial direction. The middle stages require very little editing, running within reference boundaries. Then intervention peaks again at the final stage. That final spike is for alignment. The user is checking the end of the pipeline against the decisions made at the start, debugging any drift that occurred in between. Human oversight concentrates on two specific points: initial creative direction and final alignment. This level of traceability makes semantic debugging possible. If a script sounds wrong at the end of a pipeline, you could fix that document, but that only solves the problem for a single run. If you trace the error back to the source and update a voice guide in a reference folder, you fix that behavior for every future run. The file system orchestrator makes in-source-level traceability native to the workflow. When we look ahead, the future of AI agent orchestration is not a chaotic web of complex programmatic routing code. It is a discipline of data architecture, built directly on the standard computer file system.